Okay guys, so in this video lecture I'll be talking about more on the calculation part of geometrical isomer, and I'll be throwing some of the formula in front of you, which I personally feel is not that worth remembering, but just for the sake of documentation and just for the sake of if you want to remember it, you can just remember it, but this is just very optional, right? So if you please to remember it, then please remember it. But from an exam perspective, I actually believe that you should draw and check the number of geometrical isomers then and there itself for getting more clarity. Okay, so we'll just be looking into calculation of geometrical isomers. Geometrical isomers. Okay, so the case one is if both ends are different. So if both ends of a compound are different, both ends are different of a compound, so the answer is straightforward, 2 to the power n, where n is the number of stereogenic area of pi bond which shows geometrical isomerism. It can be pi bond or ring or cumulene or any of those structures we mentioned in the first lecture when we were discussing geometrical isomerism. Okay, so where n is a number of stereogenic area of pi bond which shows, okay, so to be more clear, it can be pi bond or ring, cumulene, anything, right? Okay, so the case 2 is when we actually have, if both the ends of a compounds are same, right, as was the case when we just saw the last example or last few example in last second or third example in the last video tutorial, that we actually had 3 geometrical isomerism instead of 4, because one of the cis of some configuration was actually matching with the trans of another configuration by actually rotating the compound with 180 degrees. So we found that both the compounds were actually the same. So in the second case actually deals with that type of compounds. Okay, so I'll just write that if both just beg your pardon, yeah, if both the ends are same, then actually the formula goes like 2 to the power n minus 1 plus 2 to the power p minus 1. And what are n and p here is, so what is p here? So n is a total number of stereogenic area where we can find pi bond, ring, or cumulene, whatever is contributing to the geometric isomerism, total geometric isomers of the given compound. So if n is actually even, then we can say that p is n by 2, and if n is actually odd, then p is n plus 1 by 2. Okay, so in that case, in the previous case, I think n was 2 there, right? That's why we got to the answer 2 to the power 2, which is 4. But both the ends of the compounds were same in that case, hence we should apply this formula there and we should get the answer 3 if we put the values of n here and p here. Okay, so this brings us to the almost the ending part of geometrical isomers. So in the next lecture I'll be just talking about, I'll be taking up new topics, new concepts, like what is an electrophile, what's a nucleophile. So just a brief before ending this lecture, I just want to give you a brief insights into what we'll be discussing on in the next video lecture. So electrophile, as the name suggests, is electron loving. So electron loving means it is having positive charge on the compound or atom, whatever is the electrophile, right? So the electrophile can be carbonium ion, bromonium ion, nitronium ion, nitrosonium ion, diazonium ion, and things like that. And we'll also look at what is the contribution of Lewis acids, are the electrophile, are the nucleophile, what are interhalogens, are the nucleophile, electrophile. Oh, I just beg your pardon that I just forgot to mention that what is a nucleophile. Nucleophile is nothing but nucleus plus loving gives the word nucleophile, right? So any compound which is nucleophilic means it is having negative charge on itself. It can be alkoxide, methoxide, ethoxide, phenoxide, and things like that. So we'll be covering up all that thing into the next lecture, and I suppose and I hope that you like this video. And till then, good luck and goodbye.